Pick up a rock, any rock you like, hold it in your hand. Feel the weight of it. Squeeze it. Really try to push your thumb into it. You can't, obviously you can't, it's a rock. Rocks are solid. Rocks are solid. But let me ask you something. Why? I don't mean what is it made of? You know what it's made of. Atoms. Everybody knows that. I mean, why is it solid? Why can't your thumb go through it? Because here's what we know about that rock. Every atom in it is almost entirely empty space. If you took a single atom and blew it up to the size of a football stadium, the nucleus, the part with almost all the mass, would be a marble sitting on the 50-yard line. And the electrons, tiny specks, impossibly small, buzzing around somewhere up in the last row of seats. And in between, nothing. Vacuum, emptiness. So the rock in your hand is, by volume, 99.99999999999999999. 9% empty. I'm not exaggerating, I'm rounding down. And your thumb, same thing, empty. So what you've got when you press your thumb against the rock is two enormous clouds of nothingness refusing to pass through each other. Like two fogs that somehow can't merge, two ghosts that somehow can't walk through the same wall. You do this every day without thinking. You pick things up, you put them down, you sit on chairs, and stand on floors, and lean against walls. And every single one of those interactions, every time one object stops another object from passing through it, is a miracle. I don't use that word lightly. It is a miracle in the precise sense that classical physics cannot fully explain it. That is deeply strange, and the answer to why it happens is, I believe, the most terrifying single fact in all of physics. It comes down to one property of one particle, one tiny, abstract, invisible feature of the electron. Change that feature by even the smallest amount, and your rock disintegrates, your hand disintegrates, the chair you're sitting on, the floor beneath it, the building around you, the earth itself, every star in the sky, all of it collapses into a formless, featureless mush. Everything you have ever touched, everything you have ever seen, every object that has ever existed is standing on the edge of a cliff. And the only thing keeping it from falling off is one rule that one particle follows. So let's find out what the rule is. And let's start with something so simple you'll think I'm wasting your time. Take the simplest atom in the universe. Hydrogen. One proton sitting in the middle, one electron somewhere around it. I say somewhere because the electron is not orbiting like a tiny planet. I know you've seen that picture in textbooks, little circles with dots running around them like a miniature solar system. Forget that picture. It's wrong. The electron is more like a fog. A cloud of probability. Doesn't have a position until you look. You can only say there's a certain chance of finding it here and a certain chance of finding it there. The cloud is thickest close to the nucleus and fades as you move outward. In hydrogen, that cloud settles into the lowest energy state it can find, the most compact, most stable configuration. We call it the ground state, the 1s orbital. The electron parks there as close to the nucleus as quantum mechanics allows, and life is simple. Quiet, unremarkable. Now let's build helium. Add a second proton to the nucleus, toss in 2 neutrons for stability, and add a second electron. Both electrons settle into that same ground state orbital. Both of them fit. The cloud gets a bit tighter because the nucleus is now more strongly charged, pulling harder. But the basic picture is the same. 2 electrons, 1 orbital ground state. They're like 2 people sharing a park bench. Slightly crowded maybe, but it works. So far, nothing interesting has happened. You're probably wondering when I'll get to the point. Be patient. Now add 1 more proton, 1 more electron. Lithium, element number 3. And something happens that should make you sit up straight. That 3rd electron does not join the other 2. It can't. It's not allowed. Something in the deepest structure of reality reaches in and says, no, you may not sit here, go find another seat. And the 3rd electron is exiled to a higher energy state. The next shell out, farther from the nucleus, held more loosely, easier to strip away, like being told the ground floor apartment is full and you have to live on the 2nd floor where the walls are thinner and the wind blows harder. That matters enormously. Because helium with 2 electrons in the ground state is one of the most chemically inert substances in the universe. It doesn't react with anything, it just sits there serene and untouchable. But lithium with that 1 extra electron pushed up to a higher level is a wildly reactive metal. Drop it in water and it fizzes. It catches fire, it wants to give that outer electron away to anybody who'll take it. The difference between an inert noble gas and an alkali metal that explodes in water is exactly one electron being told, you can't sit there. Why can't it sit there? Let me show you. Every electron in an atom is described by a set of 4 numbers. Think of it as a quantum address, a unique identifier. The first number, n, tells you the energy level, roughly how far from the nucleus you are. The second number, L, tells you the shape of the orbital. Some are spherical, like a ball. Others are shaped like dumbbells or clover leaves or stranger things. The third number, mem sub L, tells you the orientation of that orbital in space, which direction it points. 3 numbers, 3 parts of the address. But there's a fourth number, and the fourth number is the strange one. It's called spin, and it has only 2 possible values, up or down, +1/2 or -1/2. That's all. 2 choices. And from those 2 choices, everything follows. Now, spin is one of the most misleading names in physics. The electron is not spinning. Not like a basketball on a fingertip, not like the Earth on its axis. If it were physically spinning, the surface of the electron would have to move faster than light, which is forbidden. Spin is not a rotation, it is an intrinsic quantum property. It has no classical equivalent. You can't picture it accurately, so don't try too hard. Just know this, every electron carries this property. It always has the value 1/2, and it can point in one of 2 directions, up or down, that's it. In 1922, Otto Stern and Walter Gerlach did a beautiful experiment. They shot a beam of silver atoms through an inhomogeneous magnetic field, a field that was stronger on one side than the other. Classical physics predicted the beam should spread out smoothly, like a flashlight beam hitting fog, smearing into a broad patch on the detector screen. Instead, the beam split into 2 clean spots, 2 and only 2. Not a smear, not 3 spots, not 5, 2. The whole laboratory went quiet when they saw the result. Because classical physics says angular momentum can point in any direction, a spinning top can tilt at any angle, there should be a continuous range of deflections. But nature said no, exactly 2. Take it or leave it. That was the first hard experimental evidence that something about the internal structure of atoms comes in exactly 2 flavors. A few years later, George Uhlenbeck and Samuel Goudsmit, 2 graduate students in Leiden, in the Netherlands, proposed the interpretation. The electron itself carries a kind of angular momentum, an intrinsic twist, that can point in only 2 directions relative to any axis you choose. They called it spin. Their advisor, Paul Ehrenfest, was initially skeptical. He told them it was either very important or nonsense. He encouraged them to publish. They did, and it turned out to be very important indeed. Dirac, in 1928, derived the relativistic equation for the electron and showed that spin emerges naturally. You don't have to add it by hand. It falls out of the marriage between quantum mechanics and Einstein's special relativity. The Dirac equation predicts that the electron has spin 1/2, with 2 possible orientations. It also predicted the existence of antimatter, the positron, which was discovered 4 years later. Not a bad week's work for one equation. But the reason spin matters for our story isn't the magnetism, and it isn't the antimatter. It's what happens when you combine spin with a principle that Wolfgang Pauli announced in 1925. Pauli was a remarkable person, brilliant, sharp-tongued, famously rude. He once dismissed a paper by saying it wasn't even wrong. But he was the kind of physicist who could intimidate anyone in a room just by sitting in the front row and shaking his head. But he was also extraordinarily perceptive. In the early 1920s, everyone was staring at the periodic table and going crazy. The pattern was beautiful. 2 elements in the first row, 8 in the second, 8 in the third, then 18, then 18, then 32. Why those numbers? Bohr had a model of the atom with electrons in orbits, but the model couldn't explain why the orbits filled up. Why didn't all the electrons just fall into the lowest orbit? Edmund Stoner, an English physicist, published a paper in 1924 showing that the number of electrons in each completed shell was exactly equal to the number of distinct quantum states available at that energy level if you counted a mysterious extra 2-fold splitting. Pauli read Stoner's paper and saw the pattern. He said later it was Stoner who gave him the final clue. And the clue was this: the complicated structure of the periodic table becomes perfectly simple if you adopt one rule. No 2 electrons in an atom can have the same values of all 4 quantum numbers. Every electron must have a unique quantum address, Address: if one electron is in the state n equals 1, L equals 0, m sub L equals 0, spin up, then no other electron in that atom can occupy that exact same state. That seat is taken, the Pauli exclusion principle. 5 words that explain everything. Now you might think I'm being dramatic. 5 words that explain everything. Really, let me prove it to you. Let me walk you through it carefully, because I want you to feel how much falls out of this. Go back to helium. 2 electrons, both in the n equals 1 shell, both in the n equals 0 orbital, both with m sub L equals 0. The only thing that can differ between them is spin. One is plus 1/2, one is minus 1/2. Both spin slots filled. The ground state is now at capacity. 2 electrons per orbit, no more. So when lithium's third electron shows up, every available quantum state in the lowest shell is occupied. Every combination of quantum numbers at n equals 1 is taken. The third electron must move to n equals 2, a higher energy, a larger orbital, farther from the nucleus. And that electron pushed out to the second shell is the one that makes lithium a metal. It's the one that makes lithium reactive. It's loosely held, easy to share or surrender. That single expelled electron is the entire basis of lithium's chemistry. Continue. Beryllium has 4 electrons. The fourth fills the second slot in the n equals 2, L equals 0 orbital. Boron has 5. And now the L equals 1 orbitals start filling, the p orbitals shaped like dumbbells pointing along different axes. Carbon has 6. Nitrogen 7. Oxygen 8. Fluorine 9. Neon 10. And the second shell is full. All the quantum addresses in n equals 2 are occupied. Neon is an inert gas, just like helium. It doesn't react. It has no reason to. Its house is full. Then sodium comes along with 11 electrons, and that 11th electron, just like lithium's third, gets pushed to the next shell. N equals 3. And sodium, just like lithium, is a reactive alkali metal that explodes in water. Every step, every element is the exclusion principle, forcing electrons into the next available slot. The entire periodic table, all 100+ elements, every chemical property, every reactivity pattern, every bond type, all of it is a consequence of electrons following Pauli's rule. Before Pauli, the periodic table was a mystery, wrapped in a pattern. Mendeleev had arranged the elements by weight and noticed that properties repeated with a rhythm. 2, then 8, then 8, then 18. Chemists used this pattern brilliantly, predicting undiscovered elements and their properties. But nobody could explain why the rhythm existed. Why 2? Why 8? Why not 5 or 12? Pauli's exclusion principle answered every one of those questions in a single stroke. 2, because there are 2 spin states in the n equals 1 shell. 8, because there are 8 distinct quantum states in the n equals 2 shell. 4 orbitals times 2 spins. 18, because n equals 3 adds d orbitals and more combinations. The numbers aren't mysterious, they're counting quantum addresses. And the exclusion principle says each address gets 1 tenant. Carbon has 4 electrons in its outer shell, arranged in a specific pattern of orbitals. Those 4 electrons can form 4 bonds, pointing roughly toward the corners of a tetrahedron. That tetrahedral geometry is not a choice. It's a consequence of which orbitals are filled and which are available, which is determined entirely by the exclusion principle. And that geometry, that precise spatial arrangement, is the backbone of every organic molecule. Every protein, every strand of DNA, every sugar molecule, your cells burn for energy. Oxygen has 6 outer electrons. 2 of them are paired. 2 orbitals are available for bonding. The bonds form at an angle of about 104.5 degrees. That angle is why water is bent. And because water is bent, it's a polar molecule with a slight positive end and a slight negative end. And because it's polar, it dissolves salts, sugars, and amino acids. It's the solvent that makes biochemistry possible. The angle of a water molecule, the shape of a carbon bond, the reactivity of iron, the conductivity of copper, the inertness of gold. All of these are downstream of the exclusion principle. All of them. You are a chemical machine, an extraordinarily complicated one, but a chemical machine nonetheless. And every chemical reaction that keeps you alive, every enzyme that folds into its precise shape, every neurotransmitter that crosses a synapse, every hemoglobin molecule that grabs an oxygen atom in your lungs and carries it to your muscles, depends on molecules whose shapes are governed by electron orbitals, whose filling patterns are dictated by a rule stated by a 25-year-old Austrian in 1925. Iron has a particular electron configuration that lets the hemoglobin in your blood bond loosely to oxygen. Loosely is critical. If the bond were too strong, oxygen would stick and never let go. If it were too weak, it would fall off before reaching your cells. The bond strength is exactly right because the d orbitals of iron, shaped and filled according to the exclusion principle, create precisely the right geometry and energy level for a reversible attachment. You breathe because of the exclusion principle. Every single breath. And it goes beyond individual molecules. The reason you can smell a rose is that specific molecules fit into specific receptors in your nose, like keys and locks. Those shapes, both the key and the lock, are determined by chemical bonds, which are determined by electron orbitals, which are determined by the exclusion principle. You smell a rose because electrons obey Pauli's rule. The sentence sounds absurd, but it's not. It's exactly what's happening. But I haven't told you the really alarming part yet. But forget chemistry for a minute. Forget molecules and reactions. Let's go more fundamental. Why is the floor solid? Why doesn't your chair sink into the ground? Why does matter take up space? You might guess it's electrical repulsion. Atoms have negatively charged electron clouds on the outside, and two negative charges repel each other. When your shoe pushes on the floor, the electrons in your shoe repel the electrons in the floor, and that's what holds you up. And that's partly right. Electromagnetic forces are involved, but they're not the whole story. They're not even the main story. In 1967, Feynman, Dyson, and Andrew Lenard published a landmark paper. They sat down with the mathematics and asked, take a bunch of electrons and nuclei interacting through electromagnetic forces. Will they form stable extended objects, or will they collapse? The answer depends entirely on whether